Hello, hi. I hope this is clear. So I've been originally making this video, but I forgot to use my microphone, so there was this rather fuzzy and probably slightly distracting sound in the background. Which I thought might not be too pleasant to listen to. So this might be a fairly lengthy video. I will try to keep it as concise as possible, but what I'll be doing is discussing what makes black holes interesting and trying to clear up black holes' name, because black holes have got rather bad press in media. And by that I mean black holes are usually used as plot devices and act as weapons of mass destruction, causing the extinctions of billions of peoples on planets and eventually eating away planets themselves. And whilst, yes, a black hole being formed in a planet of significant size, whether the black hole having significant size would not be great, it is worth saying that black holes do a lot of good for the universe, and this PowerPoint will hopefully show some of this. I was going to put a video which I managed to link onto a PowerPoint presentation, but when exporting the file to turn this PowerPoint presentation into a video so I could put it on YouTube, something strange happened, so unfortunately I won't be doing that, but it's worth saying that there is a series coming out where you can find the advert on YouTube, and I'll try to put a link to the advert below this video. And in this advert, as is fairly predictable, a black hole is made on Earth by none other than CERN, it seems like, or some other group trying to do fundamental particle physics. And this black hole essentially starts destroying the world. And it's that kind of like representation of black hole where I'm trying to show, well, black holes can do a lot of good. And it's worth saying there are things in the universe where we are more likely to encounter them than black holes, and those things would actually pose a fair bit of danger. I mean, for example, the Sun in about 5 billion years will finish its main sequence phase, its outer layers will expand and it will become a red giant, and in this process the Sun will expand to such a large degree it will swallow the Earth, thus ending the Earth and causing not only mass extinction but the end of all life on the planet. It's worth saying this is in the very far distant future, so we need not worry about it, but it is worth saying even objects like the Sun can pose a danger to the Earth, and actually the Sun is a much more dangerous threat in the far, far distant future than black holes, because we're never likely to actually come anywhere near close enough to a black hole for them to be problematic to us. And black holes are actually really helpful and good for our well-being, the well-being of physics, and potentially the well-being of the human race in the long-distant future, but I'll come on to that at the end of the video. So we'll begin by looking at how black holes can form, as this seems a very good introduction to them. It also puts them into a context which people are more familiar with, as people are more familiar with stars and are more likely to have done things like astrophysics than looked at things like general relativity. So, kind of stars in their main sequence, so where they're nice and stable and are producing lots of energy through nuclear fusion, can have different masses. No matter the mass of the star, there is a force of gravity trying to make the star collapse. And to balance this, there needs to be an outward force. And this outward force comes from particles, which are emitted from the core. And these particles are released as a process called nuclear fusion happens. And in nuclear fusion, a star brings together lighter elements to make heavier elements. So in the kind of, if you like, most stable part of a star's life, so it's in its main sequence, It's mainly hydrogen which is being fused in the core to produce helium. It's worth saying for larger stars we also have a C&O cycle, but I won't be going into that here. But essentially, broadly speaking, we have nuclear fusion, which is responsible for creating the particles that generate the pressure, which prevents a star from collapsing in on itself. And we have low mass stars and very high mass stars. Now, because very high mass stars have a very large temperature, the light that they emit in the visible spectrum is shifted towards higher frequencies, and thus they look kind of blue or white. So like O and V stars are blue and white, and they're very hot and very massive stars, whereas our sun is a lot cooler than these stars in terms of temperature, and is therefore a kind of yellow whitish colour. But in all of these stars in the main sequence, we have elements being fused in the core. And for very massive stars, they'll go through then the super-red giant phase. And in this phase, they run out of hydrogen in the core, but they can start fusing helium to make things like carbon and oxygen. And then they'll eventually run out of these, not just in their core, but in their inner shells. But then they can start, because they're so massive and therefore at such a high temperature, fusing oxygen and carbon. And they can keep this going and thus fight against the force of gravity trying to make the star contract until they get up to iron, because it takes more energy to fuse iron and heavier nuclei than iron than is actually produced when you fuse these elements together. And therefore, the moment the star has a high content of iron, it can't get any more net energy out of fusion, and so there's no force to fight the inward force of gravity, and so the star collapses. And the core will collapse, and the outer layers will collapse onto the core. And the outer layers collapse with such a large amount of kinetic energy onto this very dense core that the outer layers rip themselves apart in a very violent collision, which is known as a supernova. And a supernova is an incredibly extreme event where a lot of elements which are heavier than iron are actually produced. So a lot of gold and silver and things like that are produced in supernova or similarly energetic events. But this kind of like supernova can be so extreme that it can actually completely rip the core apart. But if the core remains, it may well have collapsed into a neutron star. And a neutron star, there is a force that's a result of quantum mechanics which prevents a neutron star from collapsing. However, this force isn't infinite, and so if the core is massive enough, then gravity can overcome even this force, and the core will continue to collapse into a black hole. And so that's one way that black holes can form, by the collapse of the core of what have been a very, very massive star. But there is another way that cores can collapse. And this way requires not cores can collapse. There is another way that black holes can form. And this way requires not one star, but two stars. So, a lot of the time, when the cloud, dust and gas that stars form from collapses, it doesn't just collapse at one point. There are actually multiple regions in the cloud where the cloud begins to collapse, and that means you get kind of groups of stars. So stars which are fairly close together. So let's take an example where we've got two stars which are quite close together, and so as they evolve, they're always orbiting each other, and we call this a kind of binary system. And in this binary system, the stars might have different masses, so they'll evolve at different rates, and indeed might go through slightly different processes during their evolution thanks to the different masses. But it might be that one of the stars has kind of reached the white dwarf stage. So the core of our sun will eventually become a white dwarf, and low mass stars, they'll leave behind a white dwarf. Whereas the other star in this binary system may well be at its main sequence or red giant phase. And so we've got a white dwarf and, say, a red giant star. Now, the outer layers in a red giant star are quite loosely held onto by the star because the outer layers are so far away from the core, because the star is so huge, whereas a white dwarf might be small, but it has a huge density and therefore a very strong gravitational field strength. And so what the white dwarf might do is it might start to pull matter and gas from the kind of surface of the red giant onto itself. And so this red giant will start to lose mass, but critically the white dwarf will start to gain mass. And eventually it will gain so much mass that the core will essentially, well, I say the core, I mean the white dwarf will start to collapse, and we will have something very similar to before, but we call this type of event a type 1a supernova for historical reasons that I won't go into, partly because we class supernova based on what we observed before we actually knew what physics were going on. So kind of how supernova are classed in terms of numbers and letters doesn't always match very well with the physics that's actually going on. But we formed a white dwarf that has, we haven't formed a white dwarf, we formed now essentially a type 1a supernova has occurred, and this white dwarf will collapse into a black hole. And that's another way that kind of black holes can form. So we talked about how black holes can form. The next thing to do is to talk about what a black hole is. Black holes are sometimes defined in terms of light not being able to escape from them. And I'll come on to where this originates from in a bit, but it doesn't really help us understand why black holes are particularly interesting. In fact, it makes black holes sound exceptionally boring, because not only does it make it sound like black holes aren't really doing much, it makes it sound like we actually can't really often detect them, and so they sound exceptionally boring. But black holes are really very interesting, and not just in terms of them being the kind of like final fates of certain stars or certain outcomes of supernovae. They're interesting because they tell us a lot about how fundamentally the dynamics of matter behaves, how matter moves, and its kinematics, and also about space and time. And to understand all of that, much of the applications of black hole research to many areas of physics and even computer science, we need to therefore look at black holes from this perspective of looking at how matter and space-time interact. And for this, we need to look at general relativity. So general relativity is something that was developed by Einstein at the same time where lots of research was going to maths to enable his kind of discussion. And so what Einstein did was he rethought about what Newton considered to be the force of gravity. So Newton thought that there was a force of gravity, and he thought that there was a force of gravity because according to his laws, an object that isn't experiencing any forces will not accelerate. So if, for example, a pen is falling to the ground, it's speeding up, and therefore its velocity is changing, so it must be accelerating, and therefore there must be a force acting on it. But what Einstein said was, it depends what you mean by acceleration. Because one way to rephrase Newton's statement that an object won't accelerate if it's not experiencing any forces is to say that a object will follow the shortest path in space-time if that space-time is flat. Because if the space-time is flat, then the idea of an object following the shortest path in space-time is equivalent to the statement an object won't change velocity if there aren't forces acting on it. But what Einstein now asked is, well, what about if space-time is curved? And it turns out if space-time is curved, then then when an object is trying to follow the shortest distance in space-time and is therefore not accelerating, it will actually have to follow a path that isn't a straight line, because in curved space-time the shortest path between 2 points are not a straight line. And because it's following a curved path in space-time, it will appear to us as if it is accelerating. And so what Einstein concluded was actually an object freely moving under gravity is not accelerating, because it's still following the shortest path it can through space-time. It's just that space-time is curved. And there's actually physical and experimental reasons to think that Einstein's viewpoint is actually a better description of what's going on than Newton's idea of gravity being a force. But Einstein's picture kind of led to the kind of conclusion that an object's motion and dynamics will be dictated by the curvature of space-time. But since Newton observed that objects seemingly produce gravity, what that must mean in Einstein's picture is that matter and energy doesn't only respond to the curvature of space-time, but it can actually curve space-time itself. So matter and energy curve space-time, but how matter and energy move through the universe is dictated by the curvature of space-time. So there's this intimate link between how matter and energy are distributed in their dynamics and the curvature of space-time. And the Einstein field equations, like the one we have here, really wrap this idea up neatly into a single equation. So in this equation, we have on one side the curvature of space-time, and we've got a constant as well called the cosmological constant, which is like a capital lambda, so a triangle but with the base missing. And what this constant does is it adapts these equations to actually make the universe evolve in a way Einstein thought the universe should, because without this constant the universe evolved in a way he thought unnatural in some way. But it turns out that we actually need this constant, this cosmological constant, to describe the accelerating expansion of the universe, which kind of we say is kind of caused by dark energy, although no one really knows the cause of this cosmological constant. So dark energy is really a term demonstrating our ignorance than actually any physical understanding of what's going on, although we do have some ideas and it is something you will begin to see something of if you look at things like quantum field theory. But on the other side of this kind of field equation, we have how matter and energy are distributed. And so the equation links the curvature of space-time and the distribution of matter and energy, which is essentially related to the core idea of general relativity, that matter and energy curve space-time, and curve space-time tells matter and energy how to move, at least in the absence of any other forces. And so now we've got that, the next task for physicists was to try to solve that and to go, well, let's say we pick a particular distribution of matter and energy, what does the curvature of space-time look around it? And you determine the curvature of, well, a manifestation of the curvature of space-time is that the shortest distance from 2 points in space-time isn't a straight line. And therefore, kind of, things like Pythagoras' theorem will no longer be valid, and so the metric will start to divert from the Euclidean metric. The Euclidean metric is like Pythagoras' theorem, but written in terms of infinitesimal distances. And therefore, we end up with having to define a different metric for differently curved space-time. And if we, well, and Schwarzschild looked at a uniform object, where this object is spherical, and asked how space-time is curved, and thus what the metric looks like for the space-time outside of this uniform spherical object, and he gave us the Schwarzschild metric, which we have here. So we have a metric that describes how a spherical uniform object or curved space-time at distances outside of this object, so in empty space around this spherical object. And for objects which aren't black holes, because they're not black holes, by definition, their radius is actually bigger than a constant within the metric called the Schwarzschild radius, which has the symbol Rs. So for objects that aren't black holes, their radius is actually bigger than Rs, and because the Schwarzschild metric describes space outside of that object, that means the only part of the Schwarzschild metric which is actually is physically realised is where we take r, so the distance from the centre of the object, to be bigger than the Schwarzschild radius, because the metric only works when we're looking at r is bigger than the radius of the object, but the radius of the object is bigger than the Schwarzschild radius. And the metric in this kind of realm where r is bigger than rs still has some interesting properties, and properties that we can kind of observe and thus infer that general relativity and the Schwarzschild metric are valid. For example, we can use it to look at planetary motion, and we indeed see that, as the metric would predict, the orbits of planets around a stable star do subtly change in a way that Newtonian mechanics can't predict, or at least Newtonian mechanics says this shouldn't happen. And this subtle changing in the orbit of planets may well have very significant effects for the future of the solar system, because our solar system, for example, consists of many objects and therefore many gravitational interactions, and is therefore chaotic systems where kind of like the long-term future state of that system is highly dependent to very small changes or deviations in the physics or states like positions of the planets or their orbits. And therefore this effect of general relativity may well have drastic implications for what our solar system actually looks like in the far distant future. But anyway, for objects that aren't black holes, the only part of the metric that is actually physically realised in the world is where R is bigger than Rs. But a black hole, by definition, is an object that's formed where the matter shrinks below the Schwarzschild radius, so where the radius of the object is smaller than Rs. And it's there where we get some rather bizarre and peculiar things happening. So, for these objects, where R is less than Rs, space and time in the interior of these objects have very bizarre properties, which can be thought of as owing due to the curvature of space-time. And not only this, when we transition from outside the black hole, so where R is bigger than Rs, to inside, where R is less than Rs, space and time seem to reverse roles, as predicted by the metric, and the metric kind of gives the mass as to what is happening. The idea of switching roles is very much an analogy, but it's this kind of switching of roles which is actually responsible for the idea that light cannot escape from within a black hole, so it's very significant. And then the next thing is kind of that because in black holes the matter, at least if we ignore quantum mechanics, seems to shrink to a singularity, we have to worry about the metric across all values of R, from R is essentially 0 to outwards to infinity. But between and including R equals Rs and R equals 0, we get two event horizons. Now, event horizons can be defined physically, but an equivalent mathematical description is that an event horizon is a point at which the metric diverges to infinity, and for a black hole there are two instances where this occurs. So the first one is where R equals Rs, and this might sound like a huge problem, this metric blowing to infinity, but to check whether it is a genuine problem, look at the curvature of space-time, and because the curvature of space-time is smooth and finite, as you go from R is bigger than Rs to R is less than Rs, this kind of event horizon is problematic for physics, and it turns out we can get rid of it by changing our coordinates. So the event horizon is merely an artifact of our choice of coordinates, although the fact that we are using those coordinates, and those coordinates do seemingly result in there being an apparent horizon, does have physical consequences. So the surface of a black hole is very important, and has some very unique properties. But the other case where we have an event horizon is where R equals 0, so at the kind of singularity, and this we cannot remove by change of coordinates, because at this point the curvature of space-time seems to be infinite, and essentially all of our understanding of physics doesn't seem to work anymore, though we suspect that quantum mechanics will come in at some point between R is Rs and R is 0 to prevent the singularity ever forming, because it's worth saying general relativity doesn't take into account quantum mechanics. So, as promised, we're going to be wrapping up this video by talking about applications of black hole research. I'll be splitting this up between theoretical ideas and application-based, though theory and application is always linked very intimately, because theoretical physics is trying to either explain things that have been observed by experimentalists or those applying physical ideas, which we don't currently have a good understanding of in terms of why these things happen, or it's trying to take models which we know work, but we know should break down at some level, and trying to generalize them or fix them such that we can then predict new things about the universe for us to observe. So theoretical and applied science is very linked, but I thought it was helpful splitting the applications of black hole research into two. So firstly, as I mentioned, kind of space and time are very unusual when we look at situations where R is less than Rs. And so understanding the black hole tells us about kind of much more about the general behaviour of space-time, and as Einstein's general relativity showed, space-time, and particularly how space-time is curved, has huge effects on the dynamics of particles within space-time, and therefore having a richer understanding of space-time might well help us to predict new aspects of dynamics, which may have far-reaching applications in lots of different areas of astrophysics. So it's very important in that respect, but also kind of, it's not just that energy or matter curves space-time, but it seems, and some physicists have gone so far to say that literally matter and energy is the curvature of space-time, and therefore fundamentally everything that we interact with is the curvature of space-time, and therefore understanding the curvature of space-time helps us understand far better everything at a fundamental level. And then the other thing is that between R being less than Schwarzschild radius and R being bigger, we expect quantum effects to kick in and have dramatic implications on the internal state of a black hole, which is changing our ideas of kind of what space-time is in terms of its quantum nature, and even if there is something more fundamental than space and time, and there's huge amounts of ideas arising from so-called quantum gravity or understanding the quantum nature of curved space-time. And some of these, like string theory, may not have much applications in physics, but it's required a whole new way of looking at particular kinds of spaces that have had very significant implications on mathematics, which is why a lot of mathematicians are very fond of string theory. And the mathematics that string theory kind of produces, or kind of helps us understand better, may well have very important practical applications, even if string theory itself doesn't, or even turns out not to be, a useful theory in describing quantum gravity in our universe. And lastly, black holes, because they're so extreme environments, to understand them we need to use physics from lots of different areas, and so black hole research is a very, if you like, interdisciplinary thing within physics, encouraging people researching lots of different things that seem very disconnected to come together. For example, with Hawking, he did a lot of work on Hawking radiation, which actually led to the ideas that black holes have thermal properties, and so he developed kicked off a whole new field called thermodynamic physics of black holes, or black hole thermodynamics. And in this you bring together kind of ideas from quantum theory used in like solid state physics or particle physics, with ideas in general relativity that astrophysicists love, with thermodynamics, which is something that kind of many statisticians, many engineers, many classical physicists are very familiar with. So this melting pot of ideas is hugely helpful for encouraging people to come together, which in itself is a wonderful thing, but which also will doubtlessly bear lots of new fruit, because we have so many ideas from so many different areas coming together, we're bound to find a lot of new and interesting things, and some of those will probably have a lot of applications. Just because there are so many ideas arising from this melting pot. And we'll be talking about some of those in the next slide. So lastly, I'll be talking about applied reasons to study black holes, although as I said, these are very much linked to theoretical advances in our understanding of black holes. So the first one is that concerning the discovery of Hawking radiation. So what Hawking did was he looked at how the curved nature of space-time would affect quantum fields. So in quantum physics, when we bring in relativity, we start talking about fields moving through space-time, and we describe particles in terms of these fields. And what Hawking did was he looked at, okay, we understand these fields well in flat space-time, but how does the Schwarzschild metric alter this field? And particularly he looked at replacing the Minkowski metric with the Schwarzschild metric. And what he found was actually the kind of curvature of space-time causes, due to these quantum fields, a black hole to have thermodynamic properties and emit Hawking radiation. But the problem is that this caused black holes to slowly evaporate over time. I mean, over trillions and trillions of years, but according to Hawking's ideas, black holes should evaporate. But this Hawking radiation contained no information about anything that collapsed to make the black hole in the first place or fell in to make the black hole bigger. So due to Hawking radiation, all information concerning everything that made or fell into the black hole is destroyed. And this violates the conservation of information, and the conservation of information is fundamental to quantum mechanics and general relativity. Thus we call it this problem of black hole information paradox, because it's like, how do you bring together two theories which individually preserve information, and then together they seem to, albeit in a rather complex and multi-step way, but still destroy this information. So understanding what's happening here really requires a good understanding and a deepening in our understanding of information, and what information is, and what forms information can take, and what physical things can happen to information. And that really pushes scientists towards learning more about information theory. And information theory has huge ramifications in many fields, and therefore research into black holes is a driving force behind the deepening of something that will probably have a lot of application in many areas. I mean, the link between information theories and black holes is so strong that actually more recently Leonard Susskind, a theoretical physicist who was one of the founders of string theory, actually proposed that there's a new law of the universe that black holes demonstrate. And this new law of the universe actually makes direct reference to ideas within computer science. So we're now actually possibly finding that there are strong links between how a computer works and aspects of a black hole. And so this interdisciplinary nature of understanding black holes, and the fact that black holes require such a deep understanding of many things used in huge amounts of technical areas outside of physics, really means that research in black holes is very useful for the technical aspects of the human race, in terms of our investigation into a wide variety of things, seemingly completely disconnected to black holes. Another thing is that black holes play a huge role in galactic formation. It's not entirely clear how. We have lots of ideas, lots of mechanisms, but it seems that most very massive galaxies contain a supermassive black hole. And not only that, but the mass of an entire galaxy can be quite reliably estimated once one knows the mass of the supermassive black hole. Well, or at least the mass of the black hole at the centre. So there is a strong relationship between the mass of a galaxy and the mass of a black hole. And lots of research have led to the strong belief, general belief, that black holes do catalyse the formation of galaxies. And black holes might even play a role in how matter is distributed across that galaxy, having an impact on what kind of stars can form in different regions of the galaxy. So black holes are hugely important in terms of the evolution of galaxies, and we're still understanding more about this every day. But it just shows you that black holes are not the kind of solely destructive things that the media likes to present them as. And lastly, black holes may well be the saviour of the human race. And I say that because kind of like black hole, so if we look at kind of stars, currently stars provide most of the energy in the universe that might sustain life. The problem is stars do this by fusing light elements to make heavier elements. And as we've already seen, once you get to heavy elements like iron, you can't actually get net energy production by fusing those heavier elements together. And so, consequently, thanks to the very thing that makes stars be able to produce energy, the mechanism by which they do that, soon new young stars won't be able to form because there won't be the light elements for them to form, and there won't be enough light elements to create tons of energy through nuclear fusion from in the first place. So we'll have to find a way to get around this. Black holes do evaporate, but they evaporate very slowly, meaning there will be tons of black holes still around, of very significant size, including Sagittarius A star, the one in the centre of the Milky Way galaxy, when there are virtually no young stars being formed in the observable universe, and when we can't rely on getting energy from stars anymore. And so the question is then, can we get energy from black holes? And it turns out we can. We use something called the Penrose effect, which relies on a bit of physics called frame dragging, predicted by general relativity. And in frame dragging we can extract energy from black holes. And I won't go into the details, but classically it's kind of like taking angular momentum from black holes, because black holes are spinning, but that's a very classical analogy. But we can extract energy from black holes. And so black holes may well be the only way that humans can get the energy they require to survive in the long distant future. And, you know, given the significant mass of black holes, how long they live for, and the vast numbers of them in the universe, I say vast, I mean, you know, there's none super close by, but, you know, there's a significant number of black holes. They are extremely rare objects. There's a fair possibility that we might one day end up using black holes as a source of energy. And very well we might use that energy to bring light back into a universe where, you know, stars can't really provide us with much light anymore. So as I say, don't worry about that. That's into the long distant future. But what I'm trying to say is black holes can be hugely helpful for humanity. They're great for scientific research. They're great for research even outside of science in fields like maths and computer science. And they may well help us on a very practical and important survival basis in the long distant future. So I hope this has been a useful video. If you like this channel, please check out my other videos. I apologise for this being rather long, there was much to cover, but hopefully I've helped show you why black holes are interesting, and also hopefully help clear up their name somewhat. And it is worth saying, when I talked about the maths, I did make some simplifications, so, I hope you're not too upset with me if you read the textbook and find things are slightly a bit different, but I have hopefully given you a good idea for black holes and the kind of concepts behind them, and hopefully the maths I have shown has been helpful in that understanding. But anyway, I'll see you soon, and I'm wishing you a good week.